Hello everybody, welcome back to the fourth chapter of calculus, and today we are going to talk about how to determine what the graph looks like if you know f prime or f double prime. So that means that you have the function and you can solve for the first and second derivative, and I want to know how to use those two equations to figure out what does f actually looks like. So here we're going to discuss the following for today. Everything that you need to know about f prime, and then also everything that you need to know about f double prime. What we're going to do more specifically is look at what happens when they are equal to 0, what happens when they are less than 0, what happens if they're greater than 0, and so forth, and what does that interpret to in the original function. And then also in addition to that, we're going to talk about the first derivative test and also the second derivative test, and finally give an example to put it all together to see what that actually does for all of us. All right, so let's go ahead and get started on the first part. So here, I want to know how can we use f prime? Like, what does it mean to solve for the first derivative besides just using it to get the equation at a tangent point? So as a recap, here from last time, we said that f prime, or when f prime is equal to 0 or does not exist, it gives us the critical point. So a critical point is when you reach either a local maximum or a local minimum. So for example, over here in the graph you see on the right hand side, a critical point would be at x is equal to a, and also another critical point is at x is equal to b. Note how, again, the derivative there or the slope there is equal to 0. And in the case of does not exist, I'll give an example in just a little bit, but those are basically our critical points. Now, what I want to do is I want to look around it just to see exactly what's happening. Remember what we said, f prime is supposed to be the slope of the tangent. So in the left-hand side of A over here, right, if you look at the left-hand side of A over here, you'll notice that the tangents are basically all going to be positive because the slopes are positive. So in addition to that, to the right of B, you'll notice that all the tangents over there are also going to be all positive because the slope is increasing. So what that means as a conclusion is that if f prime is greater than 0, then that means that f is increasing. Okay, so that is going to be our conclusion, and also vice versa. If f is increasing, then that means that f prime is greater than 0. Then, if you think about what happens in between A to B over here, you'll notice that f prime is going to be less than 0 because all the values of the slopes right there of the tangent, they're going to be negative. So the conclusion in the second case is that if f prime is less than 0, then that means that f is decreasing. And also we can kind of go back with that. So if f is decreasing, then that means that f prime is going to be less than 0. So this now leads us into what is known as the first derivative test. So here's what it says. Suppose that f is has a critical number at x equals to z, and f is continuous. Then we say that if f prime changes from positive to negative at x equals to c, then what is the conclusion? Also, if f prime is changing from positive to negative at x equals to c, then what is the conclusion? So let's go ahead and draw the first illustration. Actually, we don't really need to draw it. We can see it over here, right? You can actually see it over here at x equals to a over here. That's going to be our c value. Notice that actually, well, it's not the first one, I'm sorry. We're looking at b over here. So that's going to be this scenario. Notice that what's happening is that you are going from f prime that is negative. That's everything between a to b, right? Because the slope is going to be negative, so therefore it's decreasing. Then afterwards, you are going to be increasing, and at b, the f derivative is equal to 0. So because you're decreasing to increasing, and then you have a slope of 0, then that means that you are going to obtain a local maximum. Then we can say that at f of c, there is a local minimum, actually. So I said it wrong. It was supposed to be minimum. Yeah, that's what's happening there. Now, for the second case, that's looking at what's happening over here at A. Notice that if f prime is changing from positive to negative at x equals to c, then what happens afterwards? So before A, you can see again, all the slopes are going to be positive. So that means that f prime is positive. Then afterwards, you have slopes that are negative because it's decreasing. So therefore, f prime is going to be negative. So the conclusion is that at x equals to that value, then that means you're going to have a local maximum. So that means in this conclusion, f of c, there is a local maximum. Okay. And the final case is that what if you don't change signs? What if you go from positive to 0 to positive, or negative to 0 to negative? Then in that case, there is no conclusion in that situation then. Okay. So then that means there's no conclusion. Okay. And here, just to give an illustration of the third part as to like how does that work out, you can see that the two graphs below right here, that's exactly what's happening. You have the scenario where you are going to be increasing. Okay, if you take a look at the illustration that's on the right hand side, you'll note that both of the graphs right here, both parts of C, to the left of it, to the right of it, they're both increasing. And then the slope over here at x equals to C, it is undefined because you have a vertical line there. Because of that, you're not hitting either a maximum or minimum. So then that means that there's no conclusion in this case. But whereas the first one over here, you can actually see another scenario where f prime is going to be does not exist. Because notice over here, the derivative, right, f prime of c, does not exist because we can't find a slope there. But if you go by the first derivative test, right, notice what's happening is that here f prime is going to be greater than 0 because it's increasing. Okay. And then for this one over here, f prime is going to be less than 0 because it's decreasing. So this example right here is going to be representing a local maximum because you're going from f prime that is greater than 0 to f prime that is less than 0. And in between right there, you have a critical point, meaning that f prime of c is equal to does not exist. So therefore, by the first derivative test, you have a local maximum then. So this is going to be a local max according to the first derivative test. Okay, all right. Whereas this guy right here, as we said, there's going to be no conclusion because no sign changes. Okay, now let's go ahead and move on to the second part, which is talking about how do we use f double prime? What does it mean to actually solve for the second derivative, and how does that apply to our graph? Well, according to the previous sections that we dealt with, we said that f double prime is equal to the acceleration if you know that the f of x equation, or f equation, is with respect to time. If you take the first derivative, that is going to represent the velocity, just as kind of like a stepping stone. In addition to that, what I did in the last section was created 4 cases where we look at what happens with the graph if I were to look at the velocity as positive or negative, and also with the acceleration when it's positive or negative. So let's just kind of go through each cases just to make sure that you remember them. So in the first case, I think this one right here is probably the most recognizable. If f prime is positive and f double prime is positive, that's like saying that your acceleration is positive, therefore it's increasing, and your velocity is positive, so therefore it's increasing. So that means the sketch of the curve is going to be going up like this with this kind of concavity. Then we said, okay, well, what about what happens if f prime, the velocity, is increasing, but then f double prime is negative? Well, you're still going to be increasing, but you're going to be slowing down. That's going to be this case right here in case 1. Then we said, okay, let's look at now where f prime is going to be negative and f double prime is also going to be negative. So that means that you're going to be decreasing, and you're decreasing really, really fast. So that's case number 2. And finally, f prime is going to be negative, and that means it's decreasing, but f double prime is going to be positive. So that means that you are decreasing, but you're slowing down, and that's going to be case number 3. So yes, the first derivative basically tells us that the graph is either increasing or decreasing, depending on if it's positive or negative. But when it comes to the second derivative, it's telling us about the concavity of the graph. So the conclusion is the following. Now let's go ahead and kind of link them up. In case one, you'll notice that f prime is, in case one, you'll notice that f double prime is negative, and then also f double prime is negative in case number two. Both of those cases, that is what is known as concave down, because you'll notice that both the graph looks something like this on the side. So that is going to be an example of concave down. Okay. Whereas in case number 3 and case number 4, you'll notice that f double prime is greater than 0, and that is what is known as concave up. Okay, so concave up. The easiest way for me to remember which one is concave down versus which one is concave up is that one holds water, the other one doesn't. So meaning if I take say a like a pitcher of water and then you pour it down this way, concave down, it's not going to hold water because it's going to cascade off the side. But whereas if I take a cup of water and I pour it into the concave up situation, that does actually hold water then. So that's going to be the difference between the two. Okay. So the next one is, well, what happens if f double prime is equal to 0 or does not exist? Because I like to think that there's something that's happening just like with the critical point back in when f prime is equal to 0 or does not exist. So this, if you look at what happens there, well, here is a probably better illustration as to what's happening. Notice here in this graph, underneath it, you have a graph, right, where you have f double prime is actually equal to 0. Before that, you have something that is going to be concave down, right, because it doesn't hold water. And then afterwards, you have something that's concave up. So this right here, you'll notice here that f double prime is less than 0. And then f double prime is going to be greater than 0. So here, f double prime must be equal to 0. So what that means is when f double prime is equal to 0, or in the case of does not exist, we create something where you change concavity between the graphs. So that is to say you're going from concave up to concave down, or concave down to concave up. This is what is known as a point of inflection. Okay, so point of inflection. Now, I got to be a little bit careful here and actually write this in front. It's actually what is known as a possible point of inflection, or PPOI. The reason why I say possible point of inflection is, if you look at the second example over here, you'll notice that we have f, which is a horizontal line. So that means that f prime is equal to 0, and f double prime is also equal to 0. And note that if you have a horizontal line, there's definitely no point of inflection, meaning there's no concavity change. So in conclusion, when f double prime is equal to 0 or does not exist, there is a possible point of inflection. And in order to detect if there is one, we have to make sure that there is a sign change around it, just like in the first derivative test, where we have to find out if it's a local maximum or local minimum. Okay, so now that leads us into the second derivative test, and this is going to be the last part of it before we take all of this and apply it to an actual problem. So here we say that if f prime of c is equal to 0 and f double prime of c is greater than 0, then what's the conclusion? So here is a graph underneath that is showing that situation. First, we have f prime of c is equal to 0. So that means that we have a critical point over here. So that is where you're going to either have a local maximum or local minimum. In this case, you'll notice that the concavity is going to be concave down. And then the next afterwards is also going to be concave down. So then that means that there's no concavity change. That means that it's not a point of inflection, but it's still a critical point. But the conclusion is that, hey, according to this picture, then that means that x equals to c, you have a local maximum. Okay, because specifically you have concave down, so that means that f double prime is going to be Oops, actually, I think I kind of reversed it. So over here, I think it really should say f double prime is less than 0. So that means that this guy right here, let me change it. So then because that is supposed to be for concave down right here, okay? So if f double prime is less than 0, then we have concave down. In addition to that, where f prime is equal to 0, you have a local maximum. So that's the first part of the first derivative test. Now, the second part, you can kind of guess as to what's going to happen. I'm going to have to change this guy right here because I messed up in the first part. So this time, I'm saying what happens if f prime is equal to 0 and f double prime is greater than 0? Well, here's the illustration underneath that. You can see that this is going to be f double prime is greater than 0 because you have concave up. Then the next part afterward is also concave up, where f double prime is greater than 0 because all of this holds water. But at the very bottom over here, you can see that f prime is equal to 0. So the conclusion in this case is that when both of these conditions are held true, then that means that x equals to c, you have what is known as a local minimum. And then what happens if f prime of c is equal to 0 with f double prime of c is equal to 0? Well, there's no conclusion in that case because we can't just use, because then it'll be a scenario where you have a horizontal line, so we can't apply the second derivative test then. Okay. All right, so let's go ahead and take all of this guy right here, all of these right here, and apply it so then that way you can see how this actually all works out. So what I want to do in the very end is I want to sketch the graph of y is equal to f of x of this equation over here. Let's see, x cubed minus 3x squared minus 9x plus 1 by using the information of y prime and y double prime. So meaning sketch the graph according to the first derivative and the second derivative. So here's the first thing that we're going to do. We're going to go ahead and first find y prime and y double prime, and also the local maximum the critical points and all critical points, okay, and possible point of inflections by setting y prime and y double prime equal to 0 or does not exist. Okay, so we're going to go ahead and locate those guys first and then see what we can do with them. So here in the first case, we're going to go ahead and solve for the first derivative. Y prime is going to be equal to 3x squared minus 6x and then minus 9. Then I'm going to go ahead and set that equal to 0 to locate all of those critical points, okay? Because that's where we're going to find all of our local maximum or local minimum then. So let's see, taking this guy, which is quadratic, setting it equal to 0. First, I'm going to divide everything by 3. So x squared minus 2x minus 3 is equal to 0. So x minus 3 multiplied by x plus 1 is equal to 0. So we have critical points at x equals to 3 and also x is equal to negative 1. So right there, those are our critical values. Okay. Next, I am going to do the same thing, but with y double prime, because now we're going to introduce the possible point of inflection in this case. So taking the second derivative, that's going to give me 6x minus 6 over here, if I'm looking at it correctly. Yes, and then that means that now we have to set that equal to 0. And we are now going to get x is equal to 1. And that is going to be our possible point of inflection. And I can tell you right now that we will actually have a point of inflection at x equals to 1 because y double prime is a linear function. And what that means is you are going to go from negative to positive or positive to negative. And so as a result, there is going to be a sign change then. Okay. All right. Next, afterwards, what we're going to do is we're going to create what is known as a sign chart according to where y prime and y double prime are going to be positive and negative. So we're going to take our findings over here and now find out what's happening with the derivative and also the second the derivative. Okay, so here in the first case, if you recall, y prime is supposed to be equal to x minus 3 multiplied by x plus 1. The critical values are supposed to be at 3 and negative 1. So here, I am going to kind of like draw a chart for it. So here, let's have negative 3. And then let's say that we have, oops, sorry, not negative 3. It's going to be positive 3. So let me go ahead and get rid of this guy right here and put in actually negative 1 and also positive 3. Okay, In addition to that, I'm also going to look at y double prime, which is equal to 6x minus 6. And that means that the point of inflection is going to be located at x equals to 1. So I am also going to break it at x equals to 1 over here. Okay, so here is the second part. I am going to look at y double prime and also y prime. So let's go ahead and put that in. Okay, so for y prime, I'm going to break it into 3 intervals because we have 2 critical points. So that means I need to look at this part right here. That's 1 interval. And then this part right here, that's another interval after 3, less than -1. And the last one over here is going to be between -1 to +3. And I want to know, are those values are going to be positive and negative? So here we can just go ahead and plug in a point to test it out. So let's go ahead and kind of write that on the side. When x is equal to, let's say, -2, right? Then that is going to give us -5 by plugging it into this equation, multiply by -1, which is going to give us 5. So that means that everything to the left of -1, y prime is going to be positive. Then if I want to try something that is afterwards, right, from -1 to 3, let's see, I'm going to go ahead and plug in maybe like say 0. Then I'm going to get -3 multiplied by 1, which is equal to 3. So then that means that you're going to get something that is negative. Oops, -3. So everything between -1 to 3, the first derivative is negative. And afterwards, you can plug in something that's greater than 3, but I think you get the idea. Let's say x is equal to 10. Then we're going to get 7 multiplied by 11, which is going to be 77. So that means that everything after 3, y prime is going to be greater than 0. So that means that everything is positive. So now we have an idea of the graph because it's telling me that before it's increasing, before -1, afterwards it's going to be decreasing from -1 to 3, and then after that it's going to be increasing. So that means that my graph currently looks probably something like this. Okay, but now I want to define a little bit more by looking at the concavity. So that means that I need to now take my second equation and break it into intervals just like I did in the first case. So my first interval is going to be from -infinity all the way to 1, okay? And then afterwards from 1 all the way to +infinity, plugging it into the second equation, the y double prime. Over there, if I plug in, like say, x is equal to -2, then I'm going to get -12 minus 6, which is equal to -18. So that means that the second derivative is going to be negative there. And then afterwards, if I plug in, like say, x is equal to 4, then we're going to get 24 minus 6, which is equal to 18. So then that means everything is going to be positive right there. So now we can actually take all of this to figure out what the curve actually looks like, okay? Because let's go ahead and now isolate everything to see how that works out. So before, remember, we can only tell that it's increasing and decreasing and so forth, but now we can tell the concavity according to the sign that we have in this chart. So let me go ahead and erase the top part right here, and right here, okay? All right, so here we go. Let's put it all together. For -1, okay, for x that is going to be before -1, you'll notice that the first derivative is going to be positive and your second derivative is going to be negative. So according to our chart from earlier, that means it's an increasing function that's concave down. So that means that you have to be doing something like this. Next, after, we're going to look at this part over here, where you're going to have the where you're going from the critical point to the point of inflection. Next, you're going to have a graph that is decreasing because y prime is negative, and then y double prime is positive. So that means that you are going to be decreasing concave down this way, okay? Because both are going to be negative. After that, we're going to look from 1 to 3, right? here you'll notice that y prime is negative, and then y double prime is positive. So that means that you're going to be decreasing concave up, and it looks something like this. And finally, afterwards, for everything that's greater than 3, y prime is greater than 0, and then y double prime is greater than 0. So that means that your curve is going to look something like this then. So now you can see how here at -1, you're going to have your local maximum then. Okay, and then over here at x equals to 3, you have your local minimum, right? Because here you have the slope of 0 for each one of these. And according to my second derivative test, you can see that the second derivative is negative. And also, according to first derivative test, you're going from positive to negative. Whereas for 3, you are going from negative to positive. So according to the first derivative test, you are going to have a local minimum. And according to the second derivative test, you have everything that is positive for the second derivative. So therefore, it's concave up. So therefore, it's a local minimum too. But finally, let's go ahead and put it all together. Now what we're going to do is we're going to locate all the critical points and point of inflections and absolute maximum, absolute minimum, if there are any, and then sketch it. So we're going to go ahead and take those values and plug it into our graph to see what happens. So at first, let's see, we have a local maximum at x equals to -1. So notice I'm plugging in -1 into my original equation, which is going to give me 6. Then afterwards, my point of inflection, now my point of inflection is supposed to be at 1 over here. I think I messed up in this case. So let me go ahead and change that guy a little bit. Okay. So I'm supposed to find a point of inflection, which is at x equals to 1. And if I take that and put in my original equation, which was supposed to be over here. So if I plug in 1, x is equal to 1, we're going to get 1 minus 3 minus 9 plus 1. So that looks like it's going to be -12 plus 2. So that's equal to -10. So at the coordinate of 1 comma -10, that is going to be my point of inflection where you change concavity. And then finally, we're going to go ahead and plug in f of 3 because that's where we're going to get our local minimum then. So plugging 3 into the equation, just ahead of time, I got -26. So now we can go ahead and put everything together and see how that works out. So here's the first point. And let me go ahead and make that quick modification for our second point over here. And then we can go ahead and sketch the graph. So let's see here. It's supposed to be 1. So then at 1, you're supposed to get -10. So that's going to be over here. 1 comma -10. And remember what the curve looks like according to our chart right here. So you can kind of connect it all together according to the where it's increasing and decreasing in the concavity. So my final sketch is going to look something like this. So first we're going to increase with concave down. And then afterwards, you're going to decrease with concave down. And then afterwards, you're going to decrease with concave up. And then finally, you're going to increase with concave up. So this right here will be kind of like a rough sketch of what the graph actually looks like then. All right, so that should do it. Thank you so much.